Hello. So a little forward, this is going to be some hardcore Java research. My name is An, and I'm going to be talking about dark sides of Java remote protocols. So earlier I conducted a research over several popular Java remote protocols and found a lot of overlooked and unknown attack vectors on it. Actually, from my research, 100% of the products that I do the research on are vulnerable to the vulnerabilities listed in the slides. About 7 or 8 of them, I can get RCE on it, meaning remote code execution. Products of VMware, Dell, even Apache Tomcat and IBM Websphere. So wait for it. All right. So my name is An. I'm a researcher from Vietnam, a local company called Viettel Cybersecurity. I'm specialized in application security. You may have known me from the recent remote code execution saga on the email application named Zimbra. And I also do bug bounties and vulnerability selling to ZDI and iDefense and stuff like that. All right, so let's go. About Java remote protocol. So in this talk, I will talk about IMI and CORBA. IMI in Java meanings its full name is IMI running over GIMP protocol. So it's a proprietary protocol for Java, and it's used for remote communications between Java applications. Meanwhile, CORBA is a specification that apply for many other object-oriented languages, including C++ and Java. And the Java version of CORBA is named IMI over IIOP. Oops. All right. Okay, so I'm going to be talking about IMI over GIMP and IMI over IIOP. Let's talk about GIMP first, because this is by far the most famous protocol for Java. The architecture is pretty simple. It consists of a client talking with a registry service, the DGC service, and the custom services. The custom service is where the main service, the main work is taking place. The registry is where is a special service where it keeps a records of all the service. So if you want to talk to a custom service, you have to ask the registry first for a record, and then you can know the information to connect to the custom service. And DGC is just another service for garbage collection. It isn't that important. So talking the protocol side by side, each method call in remote method invocation is composed of one pair of TCP request and response, and methods are referenced to another intermediary object. It is from the class unicast server rep, and each IMI service holds exactly one class of that type, and that class mapped to exactly one class, and that class has the remote method we want to invoke. So let's talk about the IMI under the wire. So this is the beginning of an IMI packet. It has the header, which is at the magic, the version, the protocol. And there's the operation. The operation can be call or ping. So if in case we want to invoke a method, we use the operation call. But when we want to just know it existence, we just invoke the operation ping. So this is This is where applications like Nmap, the network scanner, used to identify IMI protocol under the wire. It just invokes a ping call to the IMI service, and if it returns an if it's acknowledged the request, then it's an IMI protocol. Cool. Then there's the object ID. This will be the main identification for the IMI service. Basically, it's a unique identifier. It has a random values, which will be used to identify that service among everything else. Cool. So here you can see it in the code. It's using the object ID and the TCP socket, the socket that the server is listening on, and it composed to an object, and you search a hash table, the object table hash table, to find a matching object of that type. Right, cool. So after the object ID, we have the num and the hash. The hash is the next important identifier that is used to reference a method hash ID. This will be from a list of predefined method ID that we define from when we code the application up. And the num, there's also the number. This is stand for the number. It's actually deprecated and not being used anymore, but this number will play a very important part in one of the attack vector that I will be mentioning next. Right, so we know that the information needed to invoke an IMI service is the object ID and the target method hash. So how do you invoke the registry and the DG service? So these are the special services, and they have the pre-known to the client. They have well-known object ID and method hash, so you can just compute it beforehand and then invoke it afterwards. Yeah, method hash can be calculated from the method description. And next, the next most important point is after it get the corresponding method, it will construct the arguments and then pass it to the method invocation. The server then passes, compute the return value and passes back on the wire. So given this is a network protocol and this is coded in Java, how do arguments and return value are unmarshaled? Unmarshaled meaning to switch from the higher layer point of view to the wire. So yeah, this is exactly what Java serialization is built for. So that's what I'm going to be talking about next, deserialization exploits. So past exploit, the most well-known exploit in the past is from Moritz Betzer. He's released a registry exploit on the registry service in 2016 and exploit unsafe deserialization. It has a couple of downsides in that it only works with the registry service part and it is fixing things JRE 8U 1-to-1. So there's also the DGC exploit. This is a lesser known than the registry service, but it is actually the better one because this service we can invoke this service from every port in the server application. Because if the code in the Java runtime compare if the object ID is equal to DGC ID, then it will make the transport into null, meaning to skip the transport check, meaning we can invoke it on any server port. And this is also fixed in 8 version 1-to-1. So what's special about version 1-to-1? So in version 8 1-to-1, Java runtime introduces JEP 290. So this is an API, a native API built into object input stream to impose a class whitelist check during deserialization. Meaning if you have to deserialize only types that are in the whitelist. Otherwise, it will reject the deserialization. Yeah, so before this came around, we have to use a technique called look-ahead deserialization, and it takes a lot of resources to build a look-ahead deserialization that actually works. So, okay, so this is built in for the registry service and the DGC service in Java runtime version 1.2.1. So the registry service, they basically they basically whitelist only classes that are in the IMI packages. So this is where the fun coming in. Looking for the unknown. So first bypass on the IMI registry. So it's also another gadget from Moritz Beller, but it's came around since 2016. It's been a long time, and it's not originally intended to target this attack scenario. It was originally intended to get around the blacklist bypass, blacklist class check for deserialization vulnerabilities. For example, the recent Oracle WebLogic 2.3 protocol uses this gadget to bypass the blacklist that Oracle built into the WebLogic application. Yeah, and it has a downside. It triggers outside of deserialization flow, meaning you cannot read the response from it. Yeah, you can't read the return value. You have to use an external communication channel like HTTP or DNS or something like that to read the return value. Yeah, so we know argument and return values are deserialized on the server side. So how about the client side? Yeah, so this is the first attack vector that we came up. The idea is to turn a server-side IMI call to a client-side call. So how do we do that? IMI actually has an interesting feature. It has a proxy interface. So for anyone who doesn't know about Java proxy, it's used to proxy from a method interface, an interface method call to another method call that is defined in the invocation handler. So in this case, we use the remote object invocation handler from the Java IMI package. This is in the whitelist of the registry. And so the problem is how to get from the read object call to the remote object invocation handler. Yeah. So we figure it out, and we will show it to you later. And it has one upside is that it can read the return value because the exploit is used in the deserialization flow, so it can be used as a data exfiltration channel, unlike the previous exploit. So this is the gadget in action. As you can see at the bottom of the stack trace, we are using the unicast remote object. These are all in the classes of IMI packages, and we are using the unicast remote object as a trampoline to jump into an interface method call. And at the interface method call, we can use the proxy, the remote invocation handler, to proxy it into an IMI client-side call. So when it invokes an IMI client-side, then it will invoke a read object on an unfiltered stream, meaning there's no filter on that stream. There's no class check on the stream. Yeah. So then again, we have arbitrary deserialization. So this is Oracle response. This is the issue is after JEP 290. So there is a way to prevent the attacks, and they are considered defense in depth, and they citing the official document, and they require users to manually configure a stream filter to block these chains. Okay, cool. They didn't recognize it as a vulnerability and leave it to user responsibility. And we'll see later as how well developer, how well other vendors disagree to that statement. And before that, we will talk about actually what I want, the most important attack surface that I want to talk about. This is the custom service. So besides the registry and the DGC service, there's the custom service where you invoke the real method call that you want to invoke at the beginning. And this is an overlooked attack surface. So for this, JEP 290 define that you have to manually specify a filter on the input stream, calling the Marshall input stream, to validate the invocation arguments at the unmarshal. So a little fun fact is that they are wrong in their statement. There's no remote server ref. They meant unicast server refs. And seems like that's it. There's no more documents to help developers secure their IMI instances. So again, users' responsibility. So highly likely a vendor or a product follows their recommendations. What the answer is none for every product we research on, including VMware, Dell, Pivotal, Apache, Karaf, Cassandra, etc. There are so many products that we just can't download them all and research each product. Basically, what we did is we just put a Google Doc on the search engine and then find every available product that we can find and pull it down and test it whether it's affected by the vulnerability. And for anyone curious, there is I got RCE in at least 7 or 8 of them. The one I didn't get RCE on is because there's no gadgets. There's just too little gadget space to find a working RCE chain. Yeah, so cool. But one more thing is every vendor did update their JRE version to after JEP 290, which is 1.2.1 version. So it looks like they are aware of the registry and the DGC exploits, but thought that they are the only way that IMI can be exploited. So yeah, we achieve RCE in most of them through some more gadget chains. So this is a very simple exploit analysis. It sounds complicated, but when it works under the Y, it's very simple. Recalling the IMI packet from the beginning, you just, so in this case, the argument in the real argument is the hello world string. So when you want to exploit it, you just simply replace the string object with a commons collection object or something like that, or a commons bin utils gadget or GDK only gadget, depending on the gadget space. And it's really that simple. And this is a fun example. This is a chain where I get an RC on VMware vRealize Operation Manager, and they use the IMI extensively on port 10 ports from 3000, and they use a JRE 1.2.1, and they has the commons bin utils gadget, but the direct code execution from it failed because, as you might have known, most of the gadget chains publicly available rely on a feature called silent template implement class. This will be used at an end gadget to escalate from a simple method call to a definition of malicious bytecode. So basically, the class isn't available in the product because the product uses a security manager to harden the product. So when there's a security manager, Java runtime simply rejects the deserialization of templates implement class. So I modified the bin util gadget to invoke. And by the way, this is not. From what I know, this is not public before. I modified the bin utils gadget to invoke a GDBC rotate implement getter. This is a class in core Java runtime. And this class has the ability to make a remote GNDI call. And for Java version lower than 9 version 191, there will be a CV 2018-3149 with lists from the GID icon to the remote class low exploit scenario. But again, most of the products are still under disclosure product process. So yeah, I went a little bit too far there, but that's about as far as I can get. So let's talk about another interesting scenario, attack scenario, JMX. JMX is a Java management extension. When it used remotely, it runs also over the IMI protocols. So this is the flow. Where the first client fetches a JMX IMI record from the registry, and then it calls the new client method to authenticate. So in the past, there had been an exploit on this protocol because the Java runtime didn't implement a filter for the argument string types. So this list to CV, and then if the authentication process is successful, it forks a new IMI listener, and then it connects to the fork IMI service and invoke the actual JMX methods that we want to invoke. So the fork service has random object ID. So as I said, object ID is what identifies an IMI service. So if one can brute fork that object ID during the service time span, he can bypass the authentication, usually meaning RCE. But that's not really practical because object ID is random enough not to be brute forkable. And surprise, the fork IMI service does not have any filter implemented. So anyone after authentication can achieve arbitrary deserialization. So this bug was acquired by a vendor called iDefense. So they purchased the bug. And but actually, it turns out that after JRE 10, there's that attribute that you can specify to whitelist a class that you can deserialize on the JMX after the JMX for the JMX services. But there's no document, absolutely no document for that attribute. And the latest JRE version 8 still has no way to prevent that. It doesn't have that attribute. So it still counts as a vulnerability, from what I think. Yeah, so cool. That's about IME over GRMP. So this is a lot of more complex, the CORBA protocol. So as I said, Java's CORBA implementation is called IMI over IIOP. IIOP is the protocol that it's running on. So CORBA provides native API. The CORBA specifications provide native API to unmarshal simple object structures that is only known to the CORBA protocols, like primitives, integer, and stuff like that, strings, and CORBA objects. CORBA object is not to be confused with Java object. They're different things. But since version 2.3, CORBA allows more complex language-dependent object types. Yeah. See what is going on here? So there's the smell of deserialization exploit again. So this is actually not related to the object input stream that we usually see, but internally, the CORBA input stream will use the same deserialization or serialization mechanism. So it's not related to the object input stream. So they can have, so it's not affected by the JEP 290 update. So meaning this is not known to any vendor at the time. Serialization, yeah. So let me showcase an interesting example, IBM Websphere. Websphere application server. It's a very popular web application server, and it's used IMI or IOP extensively on default ports, like the 4 ports you see on the screen. IBM modified the whole API for CORBA in Java runtime to its own com.ibm.imi.iop. So they did do it for implementing their own authentication mechanism. So our goal here is to find a place that handles a CORBA 2.3 object and happens before authentication, because we need pre-authentication remote code execution, right? So we reverse the protocol and find some places that many places that have that behavior. So this is the class that will be an interceptor between the IMI call and the authentication mechanism. It will so basically, it has an additional field that accepts some arbitrary alter data. Alter data doesn't relate to the stream, and then it will later call the input stream.readAny, meaning the input stream.readAny later will deserialize a CORBA 2.3 object. So that's our endpoint. Cool. So where to go from here? We still need to find a suitable gadget to escalate from here into remote code execution. But IBM CORBA is very hardened. They remove the silent templates, implement serializable capability completely. And they have very strict class loader, providing only needed classes at runtime. So they minimize the gadget space as much as possible. But still, the library is huge. So we dig deep and we found several interesting gadgets. So this is one of the gadgets. This is a gadget, but not actually in IBM code base. It's in the Apache Access code base. It will provide us the ability to do an arbitrary file on the server, but the content can only be serialized data. So the first thing I think of is to construct a web shell and write it on the web directory of Websphere. But it doesn't work because the serialized data will have the first byte as not text data. So IBM didn't recognize this as a valid GSP file. So it rejects handling it. So it's kind of unfortunate, but it can still be used to, for example, override web.config and then make the application unusable. Denial of service, I mean. Okay, so another interesting gadget that can lead to co-execution is that you can instantiate arbitrary class in any jar package via wrapper protocol. So meaning you can get from any GNDI, not GNDI, because there are a lot of GNDI calls in the IBM code base. So basically GNDI loading meaning read object in IBM cases. So you can go from any read object into the instantiate arbitrary class on the server. So this is only for file protocol. So, but we want to load a malicious class from under attacker control. So what to do? Yeah. So there's the Windows UNC file path that the previous researcher talked about. That's also pretty cool. You can wrap the file protocol over the Windows UNC file path, and then it will load the class over SMB 445 port, and then we can control the data, the classes it loads, and then RCE. But still, most of this is still under vendor disclosure, and it's the bugs won't go anytime soon because the IBM code base is very huge, and it will take a lot of time to fix all of the read object invocations. So yeah, the bug's gonna be with us for a while. Cool. So let's move on to another case: security manager or insecurity manager. So there's another previous researcher talking about this at Black Hat 16 on CORBA. Also on CORBA. So when deserializing CORBA native objects, again, this is not a Java object. This is for the CORBA protocol. It will allow, Java runtime will allow remote class loading and instantiation. So basically, this is like this gadget chain, but without the file protocol. So we can load it over HTTP or something like that. But it only works with if a security manager is present. So if a security manager is enabled and it allows, for example, outbound socket connection, this is like turn into insecure security manager. And it will lead to remote code execution. Yeah. Cool. So let's get deserialization exploit aside and moving on to something more interesting, the registry. This is one of the services that I talk about, the special service that I talk about. Attacking the registry. So the Java registry provide many operations interesting to the client. So of all of them, the most interesting one is the rebind method. So the rebind method allows you to modify an existing record in the registry into another record. Could be under attacker control. So yeah, this creates a classic man-in-the-middle attack without any of the human factor or the land factor. So, and it's fully transparent, and client has no way to know it's being eavesdropped. So what do we gain from this? So what do we gain from any man-in-the-middle attack? So imagine GMX service authentication. When service, the GMX service passes the credentials over the wire, it will most likely passes the credential over the wire. We can use this attack to capture the GMX credentials, and then it will be most likely RCE. The details will follow. And the custom IMI service as well. The VMware Websphere data protection also pass credentials over IMI connection. So, caveat, but it isn't that easy. IMI registry dispatcher, is protected by a check access, meaning it's only accessed from a address on bindable protocol. So, but actually, this access could already be a flaw in itself, because if it has local connection, it can escalate privileges. So yeah, but things doesn't stop like that. There's another overlooked and interesting one day, meaning a CVE that discovered by another researcher. So basically, the dispatcher didn't handle correctly the code flow. Meaning, if you remember the number field that I talk about in the IMI structure. So it will be used here. If the number which we can control is lower than zero, it will skip the access check code flow and then executes the method directly, meaning we can skip the local check. So CoWinderBoard and RobustGL, another researchers, discovered these months earlier, and they assigned that CVE, but they were using it for different attack vector. They were using it for a sandbox escape, so which means this attack vector is still, I believe, is still unknown at the time. And another interesting feature, an overlooked feature, one day off feature. So IMIs allow proxying over HTTP. So meaning if it detects the protocol to be HTTP. It will turn the remote host into 0000, which is a bindable interface, meaning it coming from localhost, and we can bypass the access check. But then again, another researcher reported as again a different case. They reported as a client-side request forgery, and it isn't related to this attack surface. Yeah, so it's one more interesting scenario that we can use to exploit. Cool. So let's get into action. So this is the exploit analysis. Let's just say there's a legit client, the registry, a legit service, and the attacker. So first, the attacker connects to the registry, and it modifies the legit service into its rogue agent. Cool, via the one of the two features I described earlier. And then when the legit client asks for the GMX IMI service, it will be redirected to the attacker control agent. And when the client connects, it will be connecting to the attacker, and then it will be presenting its credentials. Vulnerability pattern. So this is like basically 90% of how an IMI registry is created is using this method call. So basically, any method call that is used, any IMI registry is created using this pattern is vulnerable. So you can just like Google Doc the code here and then report a bunch of CVEs under your name. Or you can GitHub Doc or something like that. Because this is like 90% of how registry is created. Cool. So let's get to RCE. So if threats, actually I don't have much time left, so let's skip the unnecessary thing. So if you have the read-write privilege, which is the most widely used privilege in GMX protocol, you can manipulate existing available ambins, which is like the available GMX methods, to escalate into remote code execution. So Tomcat, Apache Tomcat does expose one of that type. Its name is access log val, and it can be used to can be manipulated to write file into a arbitrary location. So it's the exploit in action. This is this is a signed CVE, blah blah blah, and it needs the feature to be enabled, which is unfortunately not by default. But it's a cool bug, by the way. Anyway, first you have to modify the log pattern. This is like we modify the Tomcat access log pattern using GMX. After we get the credential, we use that credential to modify the GMX login pattern to power it. This meaning we log every power header into the log buffer. Then if we invoke an HTTP request to poison the access log, then as you can see, we then send a power header with the runtime exact our payload, basically our payload for the web shell, and then you invoke the rotate access controller val rotate to write into an arbitrary location under your control. So let's get to the interesting part. Let's see a demo. Is it working? Is it working? Come on. All right. For a second. All right. So this is a. I don't know how to like move it into. Okay, cool. Okay, so this is this is going too fast. Basically, there's a Tomcat on the right side of your screen, and then an attacker screen on the left side, and it's two. You can see. Okay, so just bear with it. So basically, On the right side, a alleged client. So we invoke the exploit on the left side, and this is like the registry already binded into another instance under attacker control. And then the exploit, when we invoke the exploit, this is a alleged client, an administrator, for example, logging into his panel. Yeah, and then he logs in, and then we can see on the attacker side. Yeah, so that's on the bottom of the screen. There's the password dumping out in plain text, but that is just too hard to see. Sorry about that. All right, so we have the credentials. We have the privilege on Tomcat. And the rest is how to write a web shell on the Tomcat web root using the vulnerabilities. So yeah, that's again, it's too hard to see. Okay, so it works just like in the slide that I described. Basically, yeah. So I build a jar package that will be used to exploit, that will connect to the GMX with the credentials, and then it will invoke the GMX methods to write to a web shell. And here you go. This is where it writes. Yeah, so we now invoke the web shell, and their calculator pop up on the Tomcat side. Yeah, cool. So we get RC and Tomcat. Cool. Cool, yeah. So let's talk about right. So Oracle is actually not prepared for this because the simplest fix for this is to use a package called the single entry registry, which will prevent the registry modification. But the API is package private, meaning only Oracle can use it, meaning only the classes in the package GMX remote can use it, and any other client, any other developers can use that package. Okay, so cool. That's another interesting note. And another final attack vector we have on the registry service. So its counterpart to the CORBA protocol is a CORBA naming service. So this is a Hello World application I put up, and there's absolutely no access check, no local access check involved. So we can just freely rebind the CORBA services to anywhere we like, and we can just achieve the same results that I demonstrated earlier. Yeah, but this is actually quite not as popular as the IMI over GI, the IMI registry class. So I have yet to find a vulnerable product in my research time span. But I believe there will be one that uses this. So that's everything about my attack scenarios. So a little bit about mitigations from what I think, because I think, honestly, I think these are all pretty new to the developers side. So you need to extensive review on IMI services that include both CORBA and IMI GRMP for the serialization filter with JEP 290. But however, JEP 290, as I said, does not provide a filter API for the IOLP object stream. So then maybe you have to, I don't know, like rely on other methods until Oracle publishes one. And you also should review the application model to minimize design risk, like not letting the credentials fly plain text under this protocol. Yeah, and keep your GRE up to date. And thank you. That's my speech. That's my talk.